The median score on that exam was a 3. So I did beat the median, but that should tell you something. A lot of people get a 0 on that exam. It's a ridiculous competition. All the problems for the past 25 years, they're online. Go look them up. You'll be like, this is an undergraduate exam? Okay. It doesn't prove shit. Bragging rights. Okay, we are doing differential equations for power series. So I have a homogeneous second order differential equation. It's linear. But I know that whenever I solve second order equations, the first thing I do is I make sure y double prime is all alone. So I'm going to divide out by a2, and I'm going to write this y double prime plus some function of x, y prime, plus some other function of x, y equals 0. Now, because P is really a1 of x over a2 of x, and Q is really a0x over a2 of x, it is possible that these functions will have points where they are not defined. It's possible because I'm dividing by whatever a2 is, I'll end up with places where these functions are not analytic, where they are singular. A point x equals x0 is an ordinary point of our differential equation if both p of x and q of x are analytic at x0. Now, our original definition of analytic was this has a power series. Well, it's kind of useless to try and define something about a power series before I found a power series. So I'm going to mean this to mean the function and its derivatives exist there. So if P and P's derivatives, Q and Q's derivatives all work at this point x0, it's an ordinary point. Otherwise, x0 is a singular point of our differential equation. So points come in 2 types, ordinary and singular. But it depends on the differential equation. Here's an example. Does this differential equation have any singular points? I got to make it look right. I can't tell whether it's ordinary or singular until I find P and Q. So I need to make this differential equation into its standard linear form. So let's start there. isolating y double prime gives me this expression. There's P and Q, the coefficient functions of y prime and y, respectively. Where are they effed up? That's where they're different from each other, but where are they messed up? Where are they going to fail to exist or fail to have a derivative that exists? And, right. Clearly, this is undefined whenever x is plus or minus 5. So those are my singular points. I only need one of P or Q to be undefined at any particular singular point. It is possible that P may have different singular points than Q, but we're going to take all of them all together. Whether it's a problem with P or a problem with Q, it's a problem for either one, that's a singular point. By the way, since all of the coefficients here were polynomials, all I really need to look at is where this is 0, since that's what I'm going to divide by, right? If I isolate y double prime here, there's P of x. What's Q of x? It's 0. And 0 is perfectly fine everywhere, isn't it? 0 is a perfectly valid function no matter what x you plug in. But this is screwed up at 1. So 1 is a singular point. Even though it's only a problem with one of the two functions, it's still a problem. Not every differential equation will have singular points. This has no singular points. It is also possible that your singular points might not be real numbers. Because all of my coefficients are polynomials, the only place I will have a problem is wherever I divide by 0. When I isolate y double prime, I'm going to be dividing by that x squared plus 2. So that's the only thing I need to worry about. Where is that equal to 0? Exactly. It is important that I know where my singular points are, even if they are complex. All real values here are ordinary points, but I do have singular points, even though they aren't real numbers. So every other number that we haven't explicitly listed as singular is ordinary. That means in all of these, so far, 0 has been an ordinary point. I like that. But if it isn't, I'll pick another value. I like ordinary points. And the reason I like ordinary points is for the following theorem. If I am at an ordinary point for my differential equation, then I can find not one, but two linearly independent solutions of the form of a power series centered at x0, which converge on x minus x0 less than r, some radius. But it turns out I can tell you that radius based on the singular points. Even if the singular points are not real, but x0 is real, this is still true. So let's go back to an example we were just looking at. Here's our differential equation. The very first example we gave where I asked you what the singular points were. If I tell you that I want to look at the ordinary point, x0 equals 0, then I can find a radius of convergence. Now, this is a lower bound for that radius of convergence. It might also end up being an upper bound for the radius of convergence, but we don't know that yet. We actually have to look at the series. I can only guarantee convergence until I hit a singular point. How far away is the nearest singular point from 0? No matter which way we go, right? The singular points were -5 and 5, so the radius is 5. But if I wanted to do this at 1, well, then my radius of convergence is 4. Even though I have more room if I go to the left singular point at -5, the nearest singular point is at +5. I don't have to restrict myself to real numbers. It is not just infrequent, it is common to do this, not just for real variables, but for complex variables. Okay. How far is it from 1 plus 3i to these points? Wait a minute. Wait a minute here. I want distance in the complex plane. That means I should graph the points in question. If I look at the complex plane, one plus 3i is here. Where are my singular points? Oh, they're on the real axis. How far is it from this point to the nearest singular point? Which is the same thing. Yeah, I'm going to go the straight line distance from here to here. And the way to get that straight line distance is Pythagoras. There's my little right triangle. The vertical leg is how long? And the horizontal leg? Which makes my hypotenuse 5. I cheated. This is a 3, 4, 5 triangle. But I'm just doing distance. I'm doing Pythagoras. I'm doing the distance formula if you really want to be pedantic about it. 3i minus 0i, 1 minus 5, quantity squared, take the square root of the sum. More often, I'll see something the other way around, where my singular points are complex. Here, the singular points are plus or minus root 2 times I. But if I'm looking at an ordinary point, I might look at 1, I might look at 3, I might look at 0. I want to know the radius of convergence. Square root of 2i is going to be here. Negative square root of 2i is going to be down there. But the radius from the ordinary point 0 is going to be almost. I'm only looking at distance. Distance is always real. So, exactly. You've seen this before. I'm going to go all the way back to Calc 2 to power series again, and I'm going to look at geometric series. Again, I'm going to ask the question, where is this singular? Plus or minus. Careful, it's not plus or minus one. It's plus or minus I. And that's why it's not the square root of I. Okay. Both of you doing the same part-way thing. So I need to go up or down I. But I remember from geometric series, when I had A over 1 minus R, that was the sum A R to the n goes from 0 to infinity. Chapter 11, section 9-ish, I think, in the textbook. If I think of this as 1 over 1 minus R squared, then I can write this as a geometric series, 1 minus x squared to the n goes from 0 to infinity. But a geometric series only converges when the ratio is less than 1. There's the ratio. That's our R. I want negative x squared in absolute value to be less than 1. That's the same as x squared being less than 1. And what's the square root of 1? Say that again. The square root of 1. Yeah. So that would mean that x is less than 1. Isn't that the same radius convergence we just came up with? By looking at where this is analytic and where its singular points are. The radius of convergence comes from knowing something about the complex plane, even though that's a function that's completely real. You sneaky mother. Radius of convergence is requiring us to think in the complex numbers. Okay. If my goal is to use the theorem we wrote down, the theorem says there are two solutions that are linearly independent from each other for our differential equation. I need to find these series. I have to plug in my series. The series. What series? Well, my solution should look like that. So I'm going to plug that in to my differential equation. And then I need to plug it in. I need to plug its derivative in. I need to plug its second derivative in. I need to know the first and second derivatives of this. This is why we did what we did on Tuesday. Take derivatives of series so I could remember them. If this is y, what's y prime? Cody? That's our ratio test. That was to find the radius of convergence for a series we knew. I'm just looking at an unknown. So I said we could take the derivative one at a time. We could take the integral one at a time. I did that separate from the test. There you go. Differentiate, integrate term by term. So I'm going to take the derivative of this with respect to x. So Cn's a number, it just stays there. Remember, this is like C0 plus C1 x minus x0 plus C2 x minus x0 squared plus. So I just take the derivative like these are powers of x. Now, please notice that when I put in 0 for n, what do I get here? I get 0. So really, I could start this at 1. Because when I put in 0, I get 0. What happens when I take the next derivative? And now, if I put in 0, I get 0. If I put in 1, I get 0, right? So I could think of this sum as starting at 2. I've run out of room there. That's the same power as it is over there. 99.999% of the time, I'm going to assume that I am centering this at 0. Without loss of generality, assume x naught equals 0. That means y is Cn x to the n, y prime is Cn n x to the n minus 1, and y double prime is Cn n minus 1 x to the n minus 2. By the way, if x0 is not 0, we could do a letter substitution. Because I did say this was without loss of generality, because if x0 is not 0, substitute. T equals x minus x0. And then you'll do this whole thing in t, and it'll be centered at 0. So it is to our benefit to have 0 be an ordinary point. And I can always do some arithmetic to make 0 an ordinary point. Once I've done this, I then need to look for a recurrence relation in C's. We did this on Tuesday, where we looked at what happened as we looked at different values, and we found C going back to C0 and C going back to C1. And we saw that like the odd ones were all 0 and the even ones were something else, right? And there was a nice way to do that. Finding that relationship is the ugly, nasty, messy arithmetic part of this. But here's the best part. It's just effing arithmetic. Whew. Ready? We're going to do one all the way from scratch. Now, I am 100% sure that you know how to solve this in at least 2 other ways. So we know what the answer is going to be. I'm going to make believe I don't know any of that crap. And I'm going to assume, hey, this has a 0 as an ordinary point. Let's build a power series. By the way, since there are no singular points, what should my radius of convergence be? Then it would only converge at that spot. The radius of convergence is the distance from my center, my ordinary point, to the nearest singular point. There aren't any singular points. How far away do I go? That means I don't go anywhere and it never converges except at this spot. Infinity. I can go as far as I want in any direction. I'll never hit anything singular, right? If I can't hit anything singular, my radius is infinity. Okay. Let's go back up here. Y double prime plus Y. Okay. I said something important on Tuesday about the power series that equals 0. The only way to get a power series equal to 0 is if every single coefficient is 0. But that's only true when the left-hand side is 1 power series. So if I really want this to be equal to 0, I should manipulate that left-hand side until it's just 1 series, not 2. Which means I have to gather all my like terms. The right-hand series here is in powers of x, x to the n. And that starts with x to the 0 and x to the 1 and x to the 2. But the left series is x to the n minus 2, which means it starts with -2 and -1, and oh, that's not good. I can't just gather the coefficients because the powers don't match. I need to fix this series to make its powers match the other one. Again, I'm going back to something I said on Tuesday. I said we can re-index a series by changing n. I don't have to use n here. I could use any letter I want. I could do a substitution. I would much rather have this be x to the n. So what if we changed that? What if I said I'm going to use k wherever I see an n minus 2? I want to change it. Here's how we're going to change it. This does not change. What happens to this series? Well, everywhere you see an n minus 2, put a k. So what happens when I see an n? It would be. So I'm going to get ck plus 2. And here, I'm going to get another k plus 2 for this n. What do I get in this set of parentheses? X to the k. Now, I'm looking at this and I realize what I wrote down here does not precisely match what I wrote down earlier. Let me go back and look at the previous y prime and y double prime up here. You'll notice this one starts at 1 for y prime, and this one starts at 2 for y double prime. I used y double prime here. I shouldn't have started at 0. I should have started at 2. Hey, wait a minute. If n starts at 2, where's k start? Zero. Oh, wait a second here. Those both start at 0 and go to infinity, but the labels are different. So over here, I said I'm going to change this to start with this being x to the k. Is there any difference in the letter I use over here? If I change that n to be m or t, would it make a difference? So what if I change it to be k? I did these as 2 separate steps. You could do them both at once. I find that to be personally distressing to try and substitute 2 different k's for 2 different things in 2 different places. So I like doing them one at a time, but you don't have to. So I re-indexed the first sum. The second sum, I just changed the letter. But now everything's in terms of k, right? So let's combine all the like terms. Make this one giant sum. And when I have x to the 0, I'll have x to the 0. When I have x to the 1, I'll have x to the 1. When I have x to the 2, I'll have x to the 2. I can just take the coefficients add them together, and now the left-hand side is a single power series. I've re-indexed and rearranged. And now I'm going to say it again. If a power series is equal to 0, then the whole series must have every coefficient be 0. And that means that this must be equal to 0. For all values of k, that must be 0. I have found a recurrence relationship between the values of C. Okay. Notice it jumps by 2. It gives me CK plus 2 when I give it CK, right? It jumps by 2s. So if I gave you C0, you could do all the even ones. And if I gave you C1, you could do all the odd ones. Yes? So let's see what happens. If I start with C0, wait a minute, before I do that, let's rearrange this. CK plus 2 is equal to CK over K plus 2 times K plus 1. I'm good with that. So if I start with C0, you can give me C2. What's C2? Oh, hang on. Wait, back up. I made a mistake. Somebody find the mistake I made right there. Yes, yes, it does. Gotta make sure it's negative. So what's C2? Recursion time. It's minus C0 over 0 plus 2 times 0 plus 1, which is the same as negative C0 over 2. I wrote it as 2 times 1 though, right? And I think of 2 times 1 as 2 factorial. All right. What's C4? Negative C2 over 2 plus 2 times 2 plus 1. Yes, negative C2 over 12. But C2 is this, right? So that's the same as negative C0 over 2 factorial, and then it's times 1 over 12, right? Wait a minute, negative times negative becomes, and then I've got 4 times 3 times 2 times 1. Isn't that bottom now 4 factorial? It went from negative to being positive. It's -1 squared, right? There are 2 minus signs there. I promise there's a reason I'm writing it that way. What's C6? It'll be negative C4 over 6 times 5. 4 plus 2, 4 plus 1. Wait a minute. -1 squared C0 over 6 times 5 times 4 factorial. What's the bottom? Six times 5 times 4, 3, 2, 1. Yeah, that's 6 factorial. And then this is -1 to the third C0, isn't it? When I do C8 with a little bit of work, I'm going to get that. As a matter of fact, C2k is -1 to the k times C0 over 2k factorial. Alarm, alarm, alarm. Hey, wait a minute, I've seen this before. If I think of the sum -1 to the k, I can put that C0 out front, 2k factorial x to the 2k, because this only works when k is even, right? That is C0 cosine of x. That's a Maclaurin series that was listed in that giant list in chapter 6, section 1. Guess what happens when we do the odd ones? And I got a constant out front, don't I? When I do the odd ones, I'm going to get C1 sine x. Hey, wait a minute. C1 cosine plus C2 sine, that's the solution I would get if I did this like a second order equation. But if it's in a place where I don't know how to get the regular solutions, I can get a power series solution, and it works. We will do more of this tomorrow. Plus, we'll look at what happens with our singular points. I'll see you all then.